So always the first step of mathematical modeling is the formation of differential equations, at least in those mathematical models where differential equations are actually used, which is in most of the mathematical models. So therefore, it is important to learn how to construct or how to form a differential equations out of the conditions that you know. So that is why we have to discuss this topic before we even start discussing and solving differential equations. Let us begin. Formation of differential equations. So we'll get straight to the actual process of constructing the differential equations. What is the first step? Write the equation involving the variables involved in the differential equations. The independent variable, say it is x, dependent variable, say it is y, and all the arbitrary constants which might be there. It doesn't matter if you even include some extra arbitrary constants. In the course of solving for particular solutions of certain situations that you require, they will automatically get eliminated. But we do require arbitrary constants. Next, obtain the number of arbitrary constants in step 1. Most of the times, when we are in the process of constructing differential equations, we know how many arbitrary constants are going to be there from the very definition of the problem. Let there be n arbitrary constants. Then what happens? In step 3, we differentiate the relation in step 1 n times with respect to x. The number of times that we have to differentiate is equal to the number of arbitrary constants that exist in the equation between x and y. What happens after that? We differentiate n times, and in the last step, eliminate the arbitrary constants with the help of these n equations involving differential coefficients and the equation obtained in step 1. After doing this, after we eliminate all the arbitrary constants, the equation that is left will be the desired differential equation in its most general form. Again, all of these 4 steps, step 1, step 2, step 3, step 4, are very abstract, and it is not clear on how we actually apply these steps in order to form a differential equation. So let us go through this algorithm by actual application in a mathematical problem. The differential equation, which represents the family of curves y is equal to c1 e to the power of c2x, where c1 and c2 arbitrary constants, is which of the following options? So we have y is equal to c1 e to the power of c2x. Many times experimental data or data that is obtained by observation of phenomena can be expressed as one quantity in terms of another quantity, where some of the parts of that equation correlation between those two quantities do contain certain constants, like we have here. Y is equal to one arbitrary constant multiplied by e to the power of x into another arbitrary constants. So here, as you can observe, we have 2 arbitrary constants. Remember this equation, y is equal to c1 e to the power of c2x. Now let us go back to our algorithm's first step. Write the given equation involving independent variable, dependent variable, and the arbitrary constants. So I'll do that. I'll get y is equal to c1 e to the power of c2x. Now this is c1. c1 is multiplied by the second term. So in that sense, it is an algebraic arbitrary constant. But the second arbitrary constant is trapped inside an exponent. We want it to be an algebraic term so that we are able to eliminate it by the process of differentiation. So what do we do? In step 2, what does it ask us to do? Obtain the number of arbitrary constants. Let there be n arbitrary constants. So I will take log of that equation on both sides. We get log of y is equal to log of C1 e raised to the power of C2 times x. Now since C1 is multiplied by e to the power of C2x, we get log of C1 plus log of e to the power of C2x. This is equal to log of C1 plus, by the exponent rule of log, we get C2x log of e. Log of e is 1, so we get log of y is equal to C2x plus log of C1. So log of C1 is also a constant because C1 is a constant. And so we have obtained y in terms of x as well as some other arbitrary constants. As you can see, taking log on both sides does not change the number of arbitrary constants. The number of arbitrary constants in this equation is still 2. Differentiate the relation in step 1 n times with respect to x. So what does it ask us to do? As many number of arbitrary constants are there, that many times we have to differentiate it. So the first derivative of this equation, which is what we have to work with, gives us 1 upon y dy by dx is equal to derivative of c2x is simply c2 plus log of c1 is a constant, so its derivative is 0. What does it ask us to do? As many number of arbitrary constants are there, differentiate that many times. So we directly differentiate this equation once again. So what do we obtain? In the first side, the left hand side, we have to apply the chain rule because y is considered as the dependent variable. Minus 1 upon y square dy by dx times dy by dx plus the 1 upon y times d square y by dx square is equal to derivative of c2, which is a constant, so it is 0. What do we get? 1 upon y square dy by dx the whole square is equal to 1 upon y d square y by dx square. Now substituting this large and unwieldy term dy by dx simply as y dash, that is the first order derivative of y with respect to x is indicated as y dash, and so the second order would be simply denoted as y double dash. Then we can write this equation as 1 upon y square y dash squared is equal to 1 upon y double dash. And then what do? We multiply both sides by y square in order to get y dash square is equal to y square upon y, which is simply y, into y double dash. So we get y dash square is equal to y into y double dash. And so we have done step 4 also by eliminating the arbitrary constants by using those equations, and we get y dash is equal to y dash square. And so option D is what we get ultimately, and this is the differential equation representing the family of curves y is equal to c1 e to the power of c2x. This is the solution. This is the solution to this question. It is not the solution to the differential equation, it's the differential equation that we actually constructed. The solution was given in the question itself. And so option D is the correct option.